Welcome back to this tutorial. Now we are going to be dealing with Ohm's law. We know that Ohm's law states that the current passing through any metallic conductor is proportional to the applied potential difference across it, provided that what? The temperature and other physical quantity remain constant. So that is, the current passing through any metallic conductor is always directly proportional to the what? Applied potential difference. What Ohm's law is telling us is that phi is directly proportional to the what? To the current. So the more the current supplied to any, the more the potential difference we have, the more the current we are going to have. So if the source, you know, this one is from the source. If the source of the current is small, then the current itself will also be small. But if the current coming from the source is in high voltage, then we are going to have what? High current. That is, we have, it means that phi and I, they are directly proportional, and they are constant proportion will now be equal to what? The resistance. That is, phi is equal to IR. So it means that it depends on the current and also depends on the resistance. So it means that is the resistance of this wire is how long the wire. Let's say we have a connection from here to here, the same material, and we also have the same material for resistance and the same material of resistance here. So this one, because the resistance here is bigger than the resistance here, then the amount in which the current we supply in this one will be different from this one. This one will have larger, and this one will be what? Will have smaller one. Because if you look at this one now, the current is inversely proportional to what? Is inversely proportional to the resistance. Current is inversely proportional to the resistance. If we have high current, then we are going to have low resistance, and that is what happened here. If you have a high current supplying to any source, then it means that the resistance of that source is small. But if the resistance is big, if you have a big resistance, then we are going to have high and low current. And that example, the typical example for this is if you look at the normal charger we normally use. So if we have a very short charger and we have a very long charger, and their material is of the same, we see that the charger, the short one, will charge from faster than the longer one, because due to the what? Due to the resistance effect on it. Unless if we use another application like in which we are not going to be dealing with now. So if we join some material together and the thing is long, we see the effect of this resistance. But in this case, in case of Ohm's law, we are only dealing with what? The same material. And we say that provided this thing will always occur, provided that the temperature is constant, and also the what? The temperature is constant, and all the physical phenomenon is also constant. Now, also in this, we have what we call ohmic and non-ohmic conductor. This ohmic and non-ohmic conductor are conditions for Ohm's law to occur. So, in this course, we are just to tell you the difference between the ohmic and non-ohmic conductor. That is ohmic and non-ohmic conductor. So ohmic conductor is a metallic conductor that perfectly obey Ohm's law. They are the one that perfectly obeys Ohm's law. And this one are the what? Are the conductor that do not obey Ohm's law. If we are to draw the graph for the ohmic conductor, if we have normal metal, we are going to have something like this. We have a positive coin, we have a negative. The voltage is negative here, the voltage is positive. So we have what? This is for pure metal. If we have a pure metal, so, and if we have a solution of what? CuXO4. So because this one too, they are they conduct electricity, like example, they conduct electricity in molten form. So we also have minus V, we have V, so we have current here, we have a current here. This one is just, this one obeys what? It obeys Ohm's law. Because if you look at this one, this is a straight line graph. And we said that V is directly proportional to IR. So it means here, V is equal to what? IR. If you are to plot the graph of V against I, if you compare with the equation of straight line, we say Y is equal to mx plus C, we see that we are not going to have any intercept. In this case, C is equal to 0, and this is our Y, and this is our X. It means that our M is equal to R. So if you look at this graph, you see that this obeys Ohm's law. Then we call this ohmic conductor. These are the graph of ohmic conductor. For non-ohmic conductor, we are going to have something like this. So we are going to have current here, potential difference, and so you see this. Then this one we normally use junction diode and junction diode. So, and the other one also we can have different things. We can have diode valve, we can have neon gas. Like that, we have many examples of non-ohmic conductor. So, but what we are just trying to say here is that, so it means it depends on two things. We have the one that obeys Ohm's law, and we have the types of conductor that do not obey Ohm's law. And those that obey, we say that they are what? We call them ohmic conductor. And those that do not obey, we call them non-ohmic conductor. This is just a typical example to show us the difference between ohmic and non-ohmic conductor. And we have seen the difference between them. Since Ohm's law states that what? P is equal to IR, and we say that the more the voltage, the more the current, the more the voltage supplied to any material, the more the current it will produce. Then we are going to have a straight line graph, which we have seen here. It means that it perfectly obeys Ohm's law. But in the case of this one, this is a curved graph. So if you are to find the slope of this, we are going to have what? We are going to have another thing entirely from Ohm's law. So we say that this one did not obey Ohm's law. Then we have arrangement of what? Let's go with arrangement of resistor. If you have a resistor, this resistor, we can always have two. We can have a parallel arrangement, and we can also have a series arrangement. We can also have a parallel series arrangement. Parallel arrangement. Let's start with series arrangement. Series arrangement, parallel arrangement. We can also have series parallel arrangement. Now, for the first one, let's take series arrangement. You have so clearly we know that there will be what? There will be a potential difference across this resistor. Let's say this is resistor 1, 2, 3. Then we have voltage supply here. So across this potential difference. So we see that there is what voltage across this resistor. Now, from here, to calculate the equivalent resistor, you can say that V is equal to V1 plus V2 plus V3. From Ohm's law, we know that V is equal to what? IR. So an R is equal to R1 plus R2 plus R3. Also, I is equal to I1 plus I2 plus I3. Now, if I bring this IR can be equal to I1 R1 plus I2 R2 plus I3 R3. Now, we know that for this, according to Kirchhoff's rule, if you look at this one like this, it is only one current that is passing through this resistor. So since it is only one current passing through it, they only have different potential difference. This is V1, V2, V3. So we can say that, therefore, I is equal to I1, which is also equal to I2, which is equal to I3. So since the same current is passing through them, I can say IR is equal to I into R1 plus R2 plus R3. This I will take care of this I, then the resistor will be equal to R1 plus R2 plus R3. Let's call this one equation 1. What can we denote? We denote that in a series arrangement to occur, then there must be what? We must have different voltage passing through the resistor and the same current in the resistor. Likewise for parallel combination, parallel arrangements, for this parallel arrangement, let's say we have something like this. Let's say this is R1, R2, R3. In this case, it is only one voltage that will pass through this resistor. And from Kirchhoff's rule, we are going to have the current for this one, I1, we are going to have current here, I2, and we are going to have current here, which is I3. If I do the same thing for that one, I will later have something like 1 over R to be equal to 1 over R1 plus 1 over R2 plus 1 over R3. And this is the what? This is how to find the parallel combination of, to find the parallel arrangement of any material. So it means that if you have a series connection, then it means the current passing through it is the same and we have different voltage. For parallel arrangement, we have the same voltage but different current. So that's the difference between the two things. Now let's look at what of if we have the combination of parallel and series arrangement. Combination of parallel and series. Let's say we have Now, if you have a circuit diagram like this, then this is what we can calculate here. The first thing is we have to find the what? We have to find the series and the parallel combination. If you look at the R1 and R2, they are what? They are parallel, they are series, they are parallel combination, and this one, the equivalent of this one will give us a series combination with this. That is, let's call all this place, let's call it RA. And from here to here, let's call it RB. To find RA now, RA will be equal to, it means 1 over RA, which is, if I, if you have something like the 1 over R to be equal to 1 over R1 plus this, then R is equal to R1, R2 over R1 plus R2, which is the same thing as R1, R2 over R1 plus R2. This is our RA. So it means this one will form a series combination with this one now. We are going to have a series combination. This is now RB. This is now RA. So, which they are now in what? They are now in series. And we have a what? We have a terminal, a potential difference V passing through them. It means that the voltage across this circuit is the same. Now, this one is now in series together with each other. So we have to find the series combination, and we know from what we from our derivation, we know that if we have a series combination, it means that the current passing through them is the same. So we can just use our equivalent resistance R to be equal to RA plus RB. And we know RA to be this, we know RB to be this. This is R3 and this is this. So it's the same thing as say R1, R3 divided by R1 plus R2 plus R3. So this is how to find the combination, the arrangement of series and parallel combination. So any question given in this form, we just have to try and look at it and solve it one by one. Try to look at the parallel combination, or if you have series attaching to each other, solve the series first and solve this after that. Another thing they can ask here is, they can ask us to find the current. This one, we said that it is only one current that is passing through this circuit. But what of in case of this one? We have a parallel combination and we also have a series combination. It means that there is a current passing through here. Also, there is another current passing through here. So we can be asked to find the current passing through the resistance RB and the current passing through RA. So we are just, the first thing we need to know is, since we know the voltage across all of them, then we know the equivalent resistance of all the circuit. Then we will apply our Ohm's law that says V is equal to IR. Now we first find the current. Current will now be V over R. We find the current passing through them. Then we now go and find it for each cycle. So factor affecting resistance. Factor affecting resistance. So the first one is the cross-section area. The length is affecting the resistance. Length, because of length, the cross-section area. The temperature. And the what? And the nature of the material. These are the factors that is affecting resistance. Now, how is this thing affecting resistance? From our, if you recall, from our formula that say resistance is equal to rho L over A. From this, we know that resistance is directly proportional to the length. Resistance is inversely proportional to area. So that is, increase in resistance of a substance is increasing in the length. In the cross wire also increase. If you increase the resistance, it means you are increasing the cross wire. Also, increasing the resistance of any material is, then the area will be decreasing because they are inversely proportional to each other. Also, the temperature also depends on it. How did the temperature depend? Resistance is also directly proportional to the what? To the temperature. So, and also depend on the nature of the material. And this nature of this material, you know, from what we do, we say that resistance is directly proportional to L. Resistance is also inversely proportional to area. It is also directly proportional to temperature. If I combine everything together, then I can have this formula. So that's the factors. These are the factors that is affecting a resistance. Let's try and solve one question on this. A resistance. Now, let's look at this question. A resistance of a wire of length 50 centimeter, length of 50 centimeter, and a diameter of 0.4 millimeter. Diameter of 0.4 millimeter. And we know that diameter is equal to 2r. So diameter is equal to 2r. It means radius is equal to diameter over 2. So it's found to be 6 ohm. Our resistance is equal to 6 ohm. We are now asked to find the resistivity. Resistivity, and also we should find the conductivity. Now, from our formula, we said that resistance is equal to rho L over A. So we want to find resistivity. If we make resistivity here as subject of formula, we are going to have RA over L. But from here we can know our area. Since we know radius, we know that our area is equal to pi r squared. But r is equal to diameter all over 2, which is the same thing as pi d all over 2 square. This one is the same thing as pi d square all over 4. Now, from here, our area can be equal to what? Pi multiplied by, our diameter is 0.4 millimeter. If you convert this one into meter, the diameter is the same thing as 0.4 times 10 raised to power minus 3 meter. Now, here I have, it's two things. It's either you take the diameter and just divide it by 2, which is 0.2 millimeter, and you use pi r squared directly. We can use the 2. Let's just take the, we know r is the same thing as 0.4 over 2, which is the same thing as 0.2 times 10 raised to power minus 3 meter. So I can just say my area is pi times 0.2 times 10 raised to power minus 3 square. Then the area is what? (1.25) times 10 raised to power minus 7 meter square. So this is our area. Now, if we substitute this, the value into this, our resistance is 6 multiplied by 1.25 times 10 raised to power minus 7 divided by, then our length is 50 centimeter, which is the same thing as 50 times 10 raised to power minus 2 meter. If you convert it to meter, you know 1 centimeter is the same thing as 100 centimeter is the same thing as 1 meter. If we press this correctly, we are going to have 1.5 6 times 10 raised to power 1.5 times 10 raised to power minus 6. Ohm meter. Now, the second question said we should find the conductivity. And we know that the conductivity is equal to 1 over resistivity, which is the same thing as 1 over 1.5 times 10 raised to power minus 6, which is 0.6 times 10 raised to power 6 ohm meter or ohm meter. So this one is the same thing as 6 times 10 raised to power 7 per ohm meter. So this is the value for our conductivity. Sorry, this is power 5. So in our next video, we are going to look at the effect of temperature on a substance. So in which we are going to be dealing with the mechanical conductor, the insulator, the electrolyte. So please subscribe and like this, subscribe to this channel, and also click the like button. Thank you.